All right, guys, welcome back from Memorial Weekend. Sorry, I had a lecture scheduled for yesterday on the course outline, but I didn't connect it with Memorial Day, so we're going to be a day behind for a little while, but we will catch up. Today we're going to hit irrational numbers in the beginning of Chapter 8. So first let's define what an irrational number is. An irrational number is the set of numbers whose decimal representations are neither terminating nor repeating. What that means is that after the decimal point, it goes on forever, and it has no repeating pattern. Okay? With irrational numbers, we did things like 1/3, which as a decimal would be 0.3 repeating. That's rational because it has a repeating number. A very common irrational number that you're all familiar with is pi. 3.1415, and it goes on forever and ever and ever. Okay? Another one that comes up in mathematics is called e, the natural number. That's 2.71, and it goes on forever. There's obviously an infinite number of irrational numbers that we could create that are not ones that are standardly or commonly used, but that's what irrational numbers are. Okay, so we're going to deal with a lot with a particular type of irrational number, and that is that those are called radicals. Okay, radicals are square roots. So let's first introduce the concept of a square root. Okay, the square root is the square root of 9. We all should know this is review is 3. When general are asking for the square root of a, you're trying to find what number squares to get a. Okay, so square root of 16. What number squares to get 16? 4. Notice we always take the positive version of the thing that squares, because -4 squared would also be 16, but we always take as a convention the positive version of the answer. Now, where things get a little bit tricky, okay, is when we do things like the square root of 2. Well, there's no whole number that I can square to get 2. 1 squared is 1. 2 squared is 4. So this answer is somewhere between 1 and 2, and it actually turns out to be 1.414, and it goes on forever and has no repeating pattern and never terminates. You could plug it into your calculator. On your calculator, there is a square root button. Okay, and we're going to use that in here. Okay, so when we deal with square roots, we oftentimes want to leave our answer just in terms of the square root. So if I'm dealing with the square root of 2, I don't necessarily want to I can't actually write out the exact value of it in decimal form because it goes on forever and ever. So if I write it in decimal form, I'm going to have to round it at some point. Okay, so we're going to start off by talking about how to simplify square roots. Again, the main type of irrational number we're going to work with in this class is roots. We're not going to work with pi or e a lot in this class. So we're going to start with first a rule, a general rule of square roots. That if I have the square root of 2 things multiplied, I can split it up as 2 different square roots multiplied. So let's take an example. If I have the square root of 8, that's the same as the square root of 4 times the square root of 2. Because I can break it up that way by the rule I just gave. But what's interesting about this is I can actually take the square root of 4, can't I? The square root of 4 is just 2. But the square root of 2 can't be simplified any further because it doesn't have a whole number square root, so we just leave it as square root of 2. So this is what we call the simplified version of the square root of 8. And this is simplified because the 2 cannot be broken up into anything else. Okay, let's try a few more of these and get acquainted with this, okay? So if I did like the square root of 72, I could break that up as the square root of 9 times the square root of 8. Notice that I'm always picking to find a factor of 72 that is a perfect square. The reason I want to find This is called a perfect square because it has a whole number square root. That's what we mean by a perfect square. I want to break it up into two factors, one of which is a perfect square, and then the other one can be anything we want. Because now I can take the square root of 9. So the square root of 9 would be 3. Then I'm left with square root of 8. But if you notice, I'm not done with the square root of 8. Because the square root of 8 could be broken up as square root of 4 times square root of 2. Again, I'm looking for a perfect square factor so that I can simplify it further. So now this is 3 times square root of 4, which is 2. And then the square root of 2 cannot be simplified anymore because none of its factors are perfect squares, and it doesn't have a whole number square root. So this is 6 square root of 2. So 6 square root of 2 is actually equal to square root of 72. If you plug them in your calculator, if you plug in square root of 72 in your calculator, and then you plug in 6 times the square root of 2 in your calculator, you should get the same exact decimal representation on your calculator. That will show you that you did it correctly. So to simplify square roots, we want to find a factor. So if I did, as an example, the square root of 75, I could break that. Let's think about 75. To 75, let's divide this into two factors, one of which is a perfect square. Well, 25 is a perfect square, right? And 3 is the other factor that goes with it. So I can write this as square root of 25 times square root of 3. But square root of 25 is 5, and then the square root of 3 cannot be simplified. Because the only two factors of 3 are 3 and 1. And neither of them is a perfect square, which means that I wouldn't be able to simplify this any further. So that is done. So 5 square root of 3 is the same as square root of 75. Okay. Now we can multiply square roots using the same rule that we did before. So if I want to multiply square roots, again, we have a couple rules. Well, honestly, let's change this. Let's multiply. Let's do this all at once. Changing my mind here. Multiply and divide square roots, okay? So we have the one rule we already had, that if I have the square root of a times the square root of b, that's the square root of ab. But I also can do square root of a over square root of b, and that's the square root of a over b. So basically with multiplication and division, dividing inside the square root or multiplying inside the square root is the same as multiplying or dividing outside the square root with two separate square roots. So as an example, I could do the square root of 2 times the square root of 5. That'd be the square root of 10. This is really not super complex. And I could also do square root of 6 times square root of 12 is square root of 72. Now be a bit careful, because I need to simplify square root of 72. I'm going to rewrite that because that's not simplified. Square root of 10 is simplified because its only two factors are actually 2 and 5. And neither of those are perfect squares. But square root of 72 has a fact could break up as square root of 36 and square root of 2. Because 36 times 2 is 72. But square root of 36 is 6. And then I'm just left with the square root of 2. Okay? I can also divide square roots. Okay, and that's really pretty simple too. If I did like the square root of 75 over the square root of 3, I would get the square root of 75 over 3. Square root of 75 over 3 is square root of 25, which is 5. Square root of 25 is 5. I could also do something like the square root of 180 divided by 2, square root of 2. That'd be square root of 180 over 2 and 1 square root, which is the square root of 90. Now that's not done being broken down, because I can actually think of a couple factors of 90, one of which is a perfect square, 9 and 10. And the reason I want that perfect square is because that's going to allow me to break this down more. So square root of 9 times square root of 10 Square root of 9 is 3, and square root of 10. Okay? It's important to recognize that that square root of 10 cannot be broken down because the only two factors of 10 are 2 and 5 and 1 and 10, and none of those are perfect squares, so nothing would simplify beyond this. Okay, so that's multiplying and dividing. What about adding and subtracting? Adding and subtracting irrationals. Okay? So the big idea here is that if I have 4a plus 4, change that, 4a plus 5a, that is equal to 9a, right? If I'm using letters, I'm using this as a metaphor here in a minute. Okay? So this is very similar as if I did 4 square root of 2 plus 5 square root of 2. Do you see how the square root of 2 is kind of like the a? This is almost like 4a plus 5a. So if you have 4 square root of 2's plus 5 square root of 2's, in theory you should have 9 square root of 2's, right? So it's almost like these are like terms with the same. So we have, what we would call in math land the coefficient to the radical. Can't spell today. Too early in the morning. And all you do is add the coefficients as long as the two roots are the same. So let's do another one. If I did 8 square root of 3 minus 5 square root of 3, since these square root of 3's are the same, I can combine like terms, and this would be 3 square root of 3, because 8 minus 5 is 3. Of course, we can make it more complicated, so why not, right? And the way I could make this more complicated is if I did something like this. Square root of 2 plus square root of 8. Well, I can't combine those because they're not the same root. But notice that I can simplify this one. This is actually square root of 4 times square root of 2, isn't it? Which is 2 square root of 2. Okay? So if I do that now, whoops, why am I writing another example? I get square root of 2 plus 2 square root of 2. This 2 square root of 2 is the same as square root of 8 simplified. Well, this square root of 2 actually has a 1 in front of it, doesn't it? Everything, we don't write the 1, but it's there. So this equals 3 square root of 2 in the end. So sometimes if the roots don't match, like in this case, the roots do not match. So you can't actually combine them until the roots match. You might have to simplify one or both of them in order to get those two roots to match. So I could do one like this. 4 square root of 50 minus 6 square root of 32. I'm getting these out of the book today. This is a bit tougher. So let's just mess around here. I can turn this into 25 and 2, can't I? And I can turn this one into 16 and 2 if I'm factoring it. So this would be 4 times the square root of 25 times the square root of 2 minus 6, carrying down the 6 and the 4 here, guys, times the square root of 16 times the square root of 2. So square root of 25 is 5, square root of 16 is 4. Those are going to reduce. So I'm going to end up getting 4 times 5, which is 20, and then I have that square root of 2 chilling out there. And then I've got 6 times 4 minus 24, and I got the square root of 2 chilling right there. Now they're like terms, aren't they? Because they both have this square root of 2, and they both have this coefficient right here. So I do 20 minus 24 is negative 4 square root of 2. So sometimes you may have to actually simplify both of them. You may actually have to simplify both of them. Okay. Our last topic we're going to do in this lecture is called rationalizing denominators. Here's what this means. In mathematics, the big idea is we don't like radicals. Radical means a root in denominators. As a convention, we don't like this, so we do what we can to eliminate them. So as an example, if I had 1 over the square root of 2, we don't like that in mathematics. We like to not have the square root of 2 down here. Well, a sneaky little trick I can get rid of that square root of 2 is we have this trick in fractions that we can multiply the top and bottom by the same thing. So I'm going to multiply the top and bottom by the same number, square root of 2. Watch what happens. 1 times square root of 2 on top is square root of 2. Now, what's square root of 2 times square root of 2? Well, that's a little tricky to figure out. But square root of 2 times square root of 2 really means the same thing as square root of 2 squared, right? Because we're multiplying by itself twice. Well, the square root and the square undo each other because they're opposite operations. Square rooting is the opposite inverse operation of squaring. So these undo each other, so I really end up just getting 2. Because the 2 and the square root kind of cancel each other out in a way. And in general, this is always true. The square root of a times the square root of a will always just be a, because this is really the square root of a squared. And again, the 2 and the square root undo each other, cancel each other out. So the way we rationalize the denominator is we multiply the top and bottom by whatever that root is. Okay, let's try some more of these. So if I did square root of 3 over 5. Okay, first of all, I can break that up as square root of 3 over square root of 5, right, by our division rule. And then I want to multiply top and bottom by that root, because that's going to turn the bottom into just a 5, right? And then the top, square root of 3 times square root of 5 is square root of 15. So that's my final answer. So I've rationalized that denominator. Okay, how about this one? How about 16 over the square root of 8? Well, if I multiply by square root of 8 over square root of 8, on the bottom, I get square root of 8. On the top, I get 16 square root of 8. But I'm not done. The reason I'm not done, or my bad, what am I doing? On the bottom, I just get 8. Sorry. Because square root of 8 times square root of 8 is 8. The square roots get undone. So anyway, notice that I can do some canceling here. I can do a 1 here and a 2 there. 16 over 8 is just 2 over 1, right? So I end up with 2 times the square root of 8. But I'm not done. Why am I not done? Because notice this can be simplified further, can't it? Square root of 8. I can write that as, I'm leaving the 2 in there, square root of 4 times square root of 2. Well, square root of 4 is 2. So now if I take 2 times 2, I get 4, and then the square root of 2 is chilling there. So in that problem, we did multiple things kind of all at once. Okay. So that should get you in through section 5.4. Next video is going to be 8.1. We're going to jump to 8.1 and introduce a new topic. So I'll stop this video and we'll go to the next one. And by the way, your Easter egg is 800657. That's 800657.